time for our second keynote. And when we introduce a keynote, we're not kidding around, as he works one of the world's successful high-tech companies, ASML. They're not only a world leader in making amazing machines that power most of our technology today, but they're also a true leader in AI. And he will share a very important lessons about the pitfalls of working with AI, which he calls the AI Demon. That sounds scary, right? Let's find out. Ladies and gentlemen, Arnaud Hubaux.
Thank you for the introduction. Good morning, everyone. When I was preparing this presentation, I asked a few leaders around me, do you invest in AI and why? And surprisingly, I got replies that were like, yeah, we don't really know, we are doubting, maybe we should not. And one of them put it very nicely. He said, you know, it's like I have this small demon on my shoulder. He's whispering in my ears to just do it because everyone is doing it. And he's showing me paper from strategic consulting firm, showing me gigantic revenue forecast. If you put all the AI revenues together, you're gonna end up in trillions of new value that is being generated. And he told me, and I asked my friends, and my friends tell me, I invest in AI, I've not seen any return yet. And when I think about myself, I'm like, yeah, I don't even know what are the risks of those investments. And then he turned around and said, hey, how do you decide and how do you manage the risks? And I figured this is a great question, and this is a question I would like to answer today, at least give you my opinion there. So if I take it from the point of view of ASML, I always start thinking about my end customers. And our end customers, they can dream really big. They want to explore space and send rovers to Mars. Or they dream really, really, really small, where they want to make nanobots that will cure cancer. Or they want to solve mobility issues. They all have different dreams, but they have one thing in common. They all need chips. And those chips are made by machines that ASML is manufacturing, like this one, this lithography scanner. So if you look at this machine, the linking pin between the dream and our system is that silicon wafer. And our machines that turn the chip designs into physical chips that are produced on those silicon wafers. Now, how is the industry spinning there? That's very interesting. Chip manufacturers, they optimize for as many as possible good chips per day. So the device manufacturers can have as many good devices per day. But the way to make it happen is not just to have good chips, it's actually to have affordable chips, affordable devices. And this is where Moore's law kicks in. Moore's law is not only about having more power and doubling the power every year, it's also making it half as cheap. So once you have your manufacturers of devices producing more and new devices, it also requires new chip designs, which requires the chip manufacturers to keep on producing new types of machines. And this is how the whole industry is spinning. This is the growth engine of the industry. And then, when you have this, of course, it generates a new R&D budget, which companies like ASML can invest in focusing on their core business, which is improving litho performance. So the lithography is the steps produced by our scanners. And this is where this thinking about AI starts, because this is our leverage on the industry flywheel. And when you know that part, you can, from my perspective, focus on three things. You can use AI to reduce your costs, the cost of your machines, the cost for ASML, but also the cost of ownership for the customers. Reduce your time to market and create new types of values. So let me give you some examples there. The first example is how do you improve defect detections in microchips? If you look at the picture, the upper one in the orange part, you see it's very grainy. So it's difficult to see there if a spot is an issue with the chip or just noise in the image. But by using deep learning technologies, you can actually enhance the quality of the picture to detect more defects. Here, for instance, ramping up to 93% defect rate detection. Another very interesting example is optimizing the mask. The mask is basically the layer that contains the design of a chip, and you have many of those masks. When you don't put your design properly on the mask, it doesn't get exposed properly on the wafer. So if you look at the grayscale picture in the before part, you see in the middle there is this kind of necking. It looks a bit like a bean that you're making. This is not what you want. What you want is a straight line. And there, AI can help you again to put those assist features in the mask so that when light is shot at it, the end result is this nice straight line. Another very typical example is defect detection. Defect detection is when you are manufacturing parts like these. They, for instance, have special types of coating. And the coating must have very, very specific properties. Otherwise, the machine doesn't work. And you can use their AI techniques to segment images of those parts and classify them so that you know if there are defects, or when the part comes back from the field, for instance, and you want to run forensics analysis, you can use AI to zoom in on the areas that were damaged and then tell you why they were damaged. So this is a way for us, for instance, to reduce our costs, because then qualification of parts goes faster, and also we just spend less engineering resources on those. These are just a few examples that prove you, yes, AI can bring value. However, and this is where the AI demon kicks in, this guy is very nasty. His only purpose in life is to make you fail and steal your business. And it does it in three very simple ways. First, it makes sure that you build solutions that are unexplainable. What does it mean? If you look at ML literature, it is very sound. It is based on mathematics. So this is perfectly explainable. The issue is that the model, they will just learn from the input you give them and try to predict some form of output. And what they do is basically try to figure out a good correlation between the input and the output. And as we all know, correlation is not causation. So when it tells you, for instance, that your machine is not behaving correctly, it just tells you it correlates with these parameters. But it doesn't mean that those parameters are actually the cause of the issue. And that's the issue. On the very short term, when you go to a customer and you show them your solution and it shows, look, it is very good at flagging when things don't go well, that's right, then the next question you get from the customer is, tell me why. And then you reply, yeah, because the model knows. Yeah, this is not very satisfactory, right? You're an equipment vendor, so you should be able to explain how it behaves. So if you can't do it, you don't get your customer trust. On midterm, if you deploy your solutions, your support team will start using it. And if the machine starts sending alarms, oh, this machine is not performing well, go fix. Okay, they will take the alarm, they will go to the machine. And then what? It's broken. Tell me why I should, where I should be looking to detect the issue. But if you don't have explainability, you don't get the support your teams actually need, so they don't trust it. And last but not least, if you can't explain when the machine is performing well or not, you cannot improve its design. And this is the most fundamental issue, because if you do not understand what is causing the issue, you can't fix your design, so you can't innovate anymore. And this is a business killer. The second element is context dependence. Very easy with AI. You're in your lab, you're doing your experiments, the team gets super excited because they hit the accuracy number they were dreaming of. Then you go to your first customer. And with the system, you ship your best engineer. And this guy surely knows how to fix it. So he will tweak it, he will make it work, he will leave the customer side. Yeah, guys, I made it. Everyone is happy. And then you deploy worldwide. And it doesn't work. And usually it doesn't work because your model is sensitive to small variations where you deploy it. But you didn't think about it up front because you wanted to train everything in-house and then deploy. And there you fail. And the last one is the one we usually miss. It's a commodity. Machine learning is a commodity. AI is a commodity. And it's very easy to believe otherwise, because when you make a model, you are very happy. Because by applying machine learning, what took your engineers maybe 2, 3, 4 months to figure out, you can do in a week. So you get all juiced up and say, hey guys, we have something good here. Look, we just spent a fraction of the money, a fraction of the time, and then we have a great product. So you go to market with it. The issue is that everyone can do it as well. A guy just out of university with a master's degree in computer science or mathematics, if you give him the data, he will do it. Your customers can do it. Your competitors can do it. So you can be sure that 6 months after you have released your first product, everyone can copy it. So if you build your business value on the machine learning model, you're killing your own business. So if you read it like this, AI is providing you an explainable, context-dependent commodity, it doesn't sound too good, right? So why should I put money in that thing, right? This is a question that everyone would ask. So let me show you how you can actually go around those topics and actually, next to having a great use case, delivering sustainable innovations with AI. So let's assume you want to build a system that once the machine has produced a lot, containing multiple wafers, you want to tell the customer manufacturing execution system if everything went well. There are 4 basic steps your system can go through. You get the data coming from the system, so all the sensor readings, for instance. From there, you can calculate features, so typically physical models that give more meaning to this raw data they get. Then you can input those features into a machine learning model that will, for instance, predict okay or not okay. The output of that model can then go into a system that will tell you, well, the system is not okay because A, B, or C, or with certain likelihood of those being the root causes. And the last step is you're looking for a recurrence pattern. Is it just a one-off? Or is it an issue that is recurring? Because if it's a one-off, bad stochastic, sorry, it won't happen again. But if it is recurring, you want to maybe schedule some maintenance on that system. So you see here we have 2 colors, the blue boxes and the green boxes. The blue boxes, this is your domain knowledge. This is the unique thing you're bringing to market. The green boxes, everyone has access to. So don't bet on them. If you have to put money and time into something, it's in the blue boxes. It's in the physical features and the symptom analysis. So there you cover the ability to explain what is going on and accept the fact that it's a commodity because it is built in your design. The last part is the context-specific element. Variations in the process occur, and you know it and you should be aware of it, especially if you're in the manufacturing world where things drift. And drift is a totally normal behavior. So when you deploy the application, you have to make sure that next to your real-time prediction, you're also building some autonomous retraining system. So basically, the AI can monitor itself, knows when to retrain, to remain accurate through time. And to do that, it's also pretty simple. You just have to put a mechanism where you monitor a number of indicators that indicate if your performance is acceptable or not. If not, assemble the training set, apply the machine learning on it. So you can train one or multiple models if you want to be safe and be able to compare them, rank them by performance, and then serve the best performing one. So serving it means you just redeploy in the new real-time prediction tools you have. And to make it specific, this is also a critical point to be successful, is make sure you build that feedback loop to the customer environment. Because in this case, eventually the customer is able to tell you if the result is okay or not okay. You can think about it as much as you want as a manufacturer. The end customer decides if the result is acceptable or not. So you have to factor it in your model. So make sure that, in our case, for instance, the wafers get inspected, we get the results of the inspection from the customer, and they tell us if the quality is good or not. So it means that to be successful, machine learning needs good data. You will read it everywhere. It also needs even better models. And here that would specifically be the blue box, the feature models. I will give you an example there. Because if you don't have it, first, you don't have a business case for your own company, and you will have all kind of noise. And this is a quote that we got from our customers. They said, we tried the same approach, but we failed. And they put lots of efforts, lots of resources in it. We failed because we don't have those physical models. These are the things that make the model reliable on the long run. So what kind of features are we talking about? How is domain-specific knowledge playing a role there? Let's assume a very simple problem. You want to predict the gray dots. Just want a time series, and you want to, based on the time, where is the gray dot going to be? Approach 1, data-driven. You just look at all the historical data you have. So you look at the other colored lines you see there, and from the data you have, use your preferred regression model on time series and try to predict the gray dots. Approach number 1. Approach number 2, you say, I actually know the machine because I'm building it myself. So let's not be lazy and just give it to a machine learning model and let it figure out, but try to put some thinking into it. So in our case, for instance, I want to predict the exact same gray dot. But I know that the dot is about a part in my machine called a reticle that contains a pattern that will be exposed on a chip. And that reticle is exposed with light so that it can be exposed on the silicon wafer. And you know that by shooting light at that thing, it will heat up and it will deform. But the thing is that because you manufacture it, you kind of know what kind of deformation will be triggered based on the usage of that system. So the lines you see there, the blue and the orange lines, are heating and cooling curves of that system. So if you know the heating and the cooling curves, the gray dots, they kind of come naturally. You don't need any data to predict it. And this is how you basically, by stepping away from just easy and just go straight to the data, in your system, you build it, your domain knowledge, to make it more robust. Because the physics you know, you don't depend on the data set, you don't depend on the quantity or the quality of the data. And that's a sure way of being successful and securing that your domain knowledge is used at its best. So I showed you 3 ways to basically get rid of this AI demon and still be successful. Make the model explainable, make it context specific, so accept that there will be variations and you're ready to handle them. And the last part, maybe surprisingly, is accept that it's a commodity. If right now I had to ask you, okay, I'm here in Eindhoven and I want to go to Amsterdam. What do? I hire a crew of engineers and we build a car together, or I call a cab. Guess which one is cheaper and faster? And this is exactly what you see now happening with AI. People hire big teams of engineers with PhDs to try to build those models themselves. But in most cases, it's not necessary. If you use out-of-the-box API provided by cloud vendors or open source libraries, you already go a very long way. And actually, you realize by using those techniques that eventually what makes a difference is not the machine learning part, but the quality of your data and the quality of your models. So coming back to the question of how do you decide to invest, and then what are the risks and how do you manage them? Deciding is relatively easy. If you understand your industry, if you understand the leverage you need to make that engine grow and spin as fast as possible, focus on those use cases. And in those use cases, identify those where AI can make a difference. Once you have identified those, make sure you build a solution that is explainable and context specific. And in all your business models, assume that everyone has access to the exact same machine learning models as you. Don't make it a unique differentiator. Your unique differentiators is what will make you successful, and it's not going to be AI. Thank you.
Yes, Arnaud, thank you so much for your insights on how you're working with AI and what are some of the pitfalls, which are very important. 2 questions. First of all, you mentioned that you need to retrain your models to keep them fresh, to keep them updated with data. People starting out with AI often think that, oh, wow, we're starting with machine learning and our machines get smarter by the day. But that's often not the case.
If you don't build it in, no. Usually you think, okay, I want a data set that is as big as possible. I will throw it in my model, and when I hit the accuracy I want, I deploy it, and we should be good. I think that's a mistake. That's only the start, especially if you're thinking about real sustainable AI. They will be in production for 1, 5, 10 years. And of course, there will be variations. So you have to build in your design the ability to learn from it.
Yeah, I always like the example that there's this big data set, this big language model called GPT-3, which is trained on billions of web pages, but only until December of 2020 or something like that. So the system doesn't know yet that Joe Biden is currently the president of the United States. Yeah. So you really need to build in these self-learning aspects as well. Second and final question, you're the AI guru of the company. And AI is such a hot topic these days. So people from all over read about it in the newspaper or see it on the news. What's the most common question they ask you about AI?
Why the heck is ASML investing in it?
Really?
You guys are physicists. You don't do anything with AI. And in a way, I think they're right. I think we've been successful and are still successful today because we do work really, really hard on the physics, making amazing parts. I think that will always remain. where AI becomes very interesting is because it is able to tailor and optimize for a very specific context, which physics cannot do, or not as easily as AI. So by adding that layer on top of what we do, we can really squeeze even more performance from our systems.
Amazing. Thank you so much.
My pleasure.